No! If you're watching this, you must be clearly rest. I am watching this because I've got no friends. Last time I got the hug, I was 17. When people say socialize, what do they mean? I got no friends, and neither do you. You got no friends, and neither do I. We've got no friends, and that's why we're watching this.
Hello everyone, and welcome to Genius Hour. My name is Magnus, and today I'm here to talk to you about the physics behind a little game called Super Metroid.
Metroid, the series that defined a genre, and one of my personal favorite video game series of all time. One that creates the perfect blend between action and exploration. Created by Nintendo in the distant past of 1986, Metroid sees you take control of a bounty hunter named Samus Aran, easily one of the most badass characters in gaming history. Orphaned at a young age on her home planet of K2L, Samus was adopted by a wise race of ancient avian aliens known as the Chozo, who infused her with their DNA, enhancing her mental and physical capabilities. The Chozo trained Samus as a warrior for most of her young life, gifting her the Power Suit, an extremely advanced suit of armor that she can summon from thin air, the same suit she uses throughout all the games. As for the games themselves, they follow a unique style in which the player does not move on a linear path. Instead, they must explore the environment and find different abilities that allow them to traverse further in the game, sometimes even having to backtrack to areas they've already been in order to find new paths that they previously couldn't reach.
It was an extremely innovative gameplay style at the time, which really deserves what little praise it gets, since it was mostly overshadowed by the likes of Mario and Zelda. Most people I talk to haven't played any of the games, let alone even heard of them, which is particularly frustrating for me since it's such a great series of games. Except Federation Force. We don't talk about Federation Force.
Anyway, enough of my ranting. Let's get into what you all came here to see. So Samus has a massive arsenal of weapons and abilities. She's got stuff like the Morph Ball, Spider Ball, Bombs, Varia Suit, Gravity Suit, Light Suit, Dark Suit, Phase-On Suit, Skirt Attack, Space Jump, Speed Booster, X-Ray Visor, Echo Visor, like a million frickin' beam upgrades. And missiles. So many f***ing missiles.
I mean, seriously, how does she cram that many missiles into her arm cannon? It'd be like trying to overfill the magazine of a Nerf gun. Maybe it's like the turrets from Portal.
How do we get so many bullets in them? Like this. Plus, we fire the whole bullet. That's 65% more bullet per bullet.
But I'm not here to talk about the missiles. The ability I really want to talk about today is the Ice Beam, one of Samus's many beam upgrades. And before I begin, I just want to clarify that I'm going to be sticking mainly to Super Metroid, the third game in the series released in 1994. This is mainly for the sake of consistency and because I felt that Super would be the easiest to analyze. So with that out of the way, let's find out just how cool this weapon is. The hell was that?
So the Ice Beam is a weapon for Samus's arm cannon that allows her to freeze enemies in place, at which point they can be used as platforms to reach different areas and solve puzzles, which in my opinion is pretty damn useful, until they thaw out and resume trying to kill you. In Super Metroid it can also be combined with the Charge Beam and Power Bombs to create a shield that freezes anything it touches. What we're looking at today is how much energy it would take to pull this off. In order to do this, we first need to understand how it works. It obviously can't be freezing the enemy solid since that would almost certainly kill them. So my theory is that the Ice Beam absorbs the energy from the air, creating a shell of solid matter that contains them.
So with this idea comes the question of exactly what part of the air is being frozen. Oxygen, nitrogen, carbon dioxide, it could be one of many things. So I gave it some thought and I eventually came to the conclusion that it would have to be the easiest part of the air to freeze. Water.
More specifically, water vapor. But how do we know that there's enough of it to freeze? Well, allow me to explain. We can assume that the planet Zebes, the planet that Samus is on throughout the game, has an atmosphere similar to that of Earth, since we see Samus able to breathe the air on Zebes in the official Metroid manga. So while that's all cool and good, we still don't yet know if there's enough water vapor in the atmosphere to freeze. To answer that question, I had to take a look at the density of Zebes' atmosphere. Now, density is equal to 2 times the mass of an object times acceleration due to gravity, all divided by terminal velocity squared times projected area times the coefficient of drag.
Now, that's a lot of variables to work with just to find one value. So let's go through each one at a time just to keep this somewhat comprehensive. We'll start with gravity and terminal velocity, since those, in my opinion, were the hardest to find, so we'll get them out of the way first.
So to find gravity on Zebes, I took a look at Samus's maximum jump height without the high jump boots, since her velocity at this exact point would be 0. To do this, I found a space in-game with lots of verticality and visible tiles, so that height would be easy to measure. I had Samus jump straight up and counted how many tiles high she was at her maximum height, which in this case was 7 tiles, or 112 pixels, since one tile is 16 pixels tall. To find the height in a pixel, I took Samus's in-suit height of 1.9 meters as listed in the Metroid 2 instruction manual, and divided it by her pixel height of 48 pixels. Using this ratio, I calculated a max height of approximately 4.43 meters. And thanks to the feature of frame advancing, I was able to find out exactly how many frames it took her to reach this height, which was 46. Since Super Metroid runs at 60 frames per second, that gives us a time of approximately 0.767 seconds. Plugging in all those values and doing some rearranging results in Zebes' acceleration due to gravity being approximately 15.08 meters per second squared, just over 1.5 times that of Earth. As for terminal velocity, I used basically the same process. I'll save you the headache and just give you my result, which in this case was approximately 10.86 meters per second.
So, yeah, I understand that was probably a lot of information to absorb in such a short amount of time, and while I love to slow down, I'm bound by the otherworldly force that is the video time limit. But rest assured, the worst of it's over. That was a lie, no it isn't.
All that's really left to take care of now is projected area, since the drag coefficient is a set value, in this case 1.3 for a person in upright position. Projected area is basically just the shadow an object casts. Based on Samus' sprite and falling position, the shadow would be roughly in the shape of an oval, with a longer diameter between her elbows and the shorter diameter from her back to her chest. Coupling these pixel measurements, 41 and 12 respectively, with our previous ratio along with the formula for the area of an oval gives us a projected area of about 0.605 square meters. Now that we have all our variables, we can finally plug them into our equation to give us an atmospheric density of approximately 29.241 kilograms per cubic meter. That's just over 24 times as dense as Earth, which would mean that there's approximately 43.2 moles of water vapor per cubic meter of air on Zebes.
So to put it bluntly, there's almost as much water in the air on Zebes as there is air in the air on Earth. So I think it's pretty safe to say that there's going to be enough to freeze. And while that's great to know, we still have a lot more ground to cover. So hang on to your seats. Because we're going deeper.
So now that we know there's enough water, we need to know how much is being frozen, which thankfully was pretty straightforward. I found the largest freezable enemy I could and calculated the volume of space that they would take up. The enemy I happened to choose was the Metroid, a parasitic creature that serves as a recurring threat throughout the series of the same name. The Metroids are largely spherical in shape, so it made my job a hell of a lot easier since all I needed was its radius of 19 pixels, or about 0.752 meters. To approximate how much air was being frozen around it, I took the volume of a sphere about 2 centimeters wider and subtracted the Metroid's volume from it. I used 2 centimeters since the enemy sprite doesn't change in size when it's frozen, meaning the ice would be thinner than a pixel length, which is about 4 centimeters. So 2 felt like a good middle ground. Subtracting the Metroid's volume from such a sphere gives us a volume of 0.15 cubic meters, which translates to roughly 137.55 kilograms when multiplied by the density of ice.
So now that we know that the weapon needs to be strong enough to freeze about 138 kilograms of water, the next question is at what temperature and pressure, since a drastic enough difference in either could alter the freezing and boiling points of the water. So unfortunately, we're not quite out of this yet. We need to go deeper.
And when I say deeper, I mean that quite literally, as we're going deep under Zebes' crust and into the volcanic caverns of Norfair. Norfair is arguably one of the most dangerous locations in the game due to its extreme heat, which makes it impossible to traverse without the use of the Varia suit. Based on its subterranean nature and high temperatures, I compared it to that of a dormant volcano, whose internal temperature is typically around a nice chilly 750 degrees Celsius. Since the ice beam works just as effectively in Norfair as it does everywhere else on the planet, we have to assume that it would be outputting enough energy to freeze water vapor at that temperature. Now that we have the temperature of Norfair, we can find its air pressure using the ideal gas law equation, which is PV equals nRT, where P is pressure in atmospheres, V is volume in liters, N is moles of gas, R is the ideal gas constant of 0.082, and T is the temperature in degrees Kelvin, which in this case is 1023. Since the physics work the same here as they do everywhere else in the game, we can assume that the molar concentration of air stays the same, 24 times that of Earth, making it approximately 1.07 moles per liter. Setting volume to 1 and substituting in the rest of our values gives us a pressure of about 90 atmospheres, or 9.12 megapascals. Now, that's pretty damn high, but not quite high enough to bump the freezing point of water above 0 degrees Celsius based on this phase diagram. However, it does bring its boiling point up to 275, which will greatly affect our calculations.
Speaking of calculations, we're just about ready to calculate the final energy output of the ice beam. That's right. All this time and confusion will soon be worth it. But first, we need to go deep. Just kidding. We've got everything we need. So without further ado, let's find out just how much energy it's going to take to put these Metroids on ice. Oh, okay, seriously, what the fuck?
So to calculate energy output, we're going to need to take the sum of 4 different calculations. 1 to bring the vapor to its boiling point, 1 to change it to water, 1 to bring it to freezing point, and 1 to change it to ice. The first and third calculations make use of the equation Q equals mc delta T, or energy equals mass times specific heat capacity times change in temperature. For first calculation, heat capacity and temperature change would be 1.996 kilojoules per kilogram Kelvin and negative 475 degrees respectively. For a third, they would be 4.187 kilojoules per kilogram Kelvin and negative 275 degrees. As for our second and fourth calculations, those are simply mass times latent heat of vaporization and mass times latent heat of fusion, where LV and LF for water are 2,258 and 334 kilojoules per kilogram respectively. Plugging in all our values to their respective equations and then taking their sum gives us a grand total of approximately 645,320 kilojoules.
To give that some context, that's about the same amount of energy contained in 154 kilograms of TNT. More than the combined kinetic energy of 645 one-ton cars hitting you at 161 kilometers per hour. Over half the amount of energy contained in a bolt of lightning, all unleashed in a fraction of a second. And that's just in one shot. Terrifying? Absolutely. Realistic? No.
Hotel Trivago.
Shameless advertising aside, I think we can all agree that Samus Aran isn't someone you'd want to mess with. Her wide array of weapons and skills makes her quite the intimidating foe. But under all that, she's still a kind-hearted soul who cares for the well-being of others. One who fights for peace and justice in a galaxy ravaged by war and chaos. It's just one of the many things that I love about her character and this series as a whole.
And while I'd love to talk about Metroid all day, that's all the time I've got. So thanks everyone for watching, and I'll see you all next time. Stay classy.